They begin, Jennifer. Yes. Last time we discussed differential forms from the point of view of algebra related to the differential. There are differential forms on the manifold which, M, which form a space omega q m, or q is the degree of the form. There is a differential D, which is a linear map of omega q m into omega q plus 1 m, satisfying also some algebraic properties. But from the point of topology, the most notable property is that d squared is 0. That is, if you apply d twice to a differential form, you get 0. By this reason, we have a certain inclusion. The terminology which we also used here is forms which are annihilated by a differential. By the differential are called closed forms. And forms which belong to the image of the differential, which are differentials of other forms, are called exact forms. D squared is 0 shows and actually is equivalent to the fact that every exact form is closed. And there are immediate examples which show that closed forms are not necessarily exact. The example which we have immediately is a trivial example, but there are more interesting examples. The example which we have immediately is that a constant function regarded as differential form of degree 0, so belonging to omega 0 m, belongs to the kernel of the differential, because differential of the constant function is 0. This is one of the most fundamental properties of derivatives. Forms of degree 0 cannot be exact because there are no non-zero forms of degree -1. So a constant function is the first, maybe 0th, maybe negative first example of a closed form which is not exact. There are other examples, and I hope I will be able to speak of them. So again, from the point of view of topology, if we are interested in topological invariance of manifolds, forms and their differentials actually comprise a very strong and very efficient set of tools. But from the point of view of analysis, differential forms exist not for taking differentials. At least it is not the first thing. Differential forms like p dx plus q dy appear in calculus, and by absolutely different reason. This is because we can use this expression p dx plus q dy as an integrand. We can integrate it. Speaking of p dx plus q dy, we can integrate this, let me say, expression, although I already told you that I didn't know what it is. And this expression can be integrated over an oriented curve in the plane, and you get a number. Actually, from the point of analysis, differential forms exist for integrals. This is material to integrate. And this is what I want to discuss today. So I will begin with the following thing. I will write something on the board, but let me just say what I'm going to do. Suppose that we have an orientable, let me say compact for now, orientable compact n-dimensional manifold. And the form also of degree n, the same degree as the dimension of the manifold. Then, without any additional fixations, there exists a well-defined number which is called the integral of the form, say it is alpha, over the manifold, say it is m. Integral sub m alpha, a real number. So again, immediately for we want that this definition is good for any differential form, we need to assume that M is orientable. We will never drop this condition. And M is compact. This condition is questionable, and we can discuss it. So a compact, orientable, oriented. Compact, oriented with fixed orientation. Manifold M, then for every form of degree n, there exists this number, the integral. Before I do that, I want to say something else about the condition of compactness. Even in analysis, you understand that if you have a non-compact manifold like a straight line, and differential form f of x dx, then the integral f of x dx over the whole straight line from negative infinity to infinity in general doesn't exist. There is a word in analysis, improper integral, conditions when still it exists, and so on. We will not go this far. But let me say that there are forms which have, as people say, compact support. This means that there exists a compact set in our manifold, such that the restriction of the form to the complement of this compact set is 0. Compact support. The form f of x dx on the straight line has compact support simply if f of x is equal to 0 outside of some finite interval. And for forms, if a form has this thing, compact support, then you can consider integrals over non-compact manifolds. Still require they are oriented. Orientation is important. Now let's discuss what the integral is. First, there is a notion analysis. If we have a form, differential form of degree n in, say, n-dimensional space or some domain in the space, this is f of x, where x is x1, xn, dx1, dxn. This wedge sign is usually not used in analysis, but otherwise this is sort of familiar. Then we have a domain U. And you assume that U bar is compact and is contained in the domain of the function f. In this case, the domain of the function f is not important, but we can assume that it is open. In this case, the integral of u f of x maybe without this wedge signs becomes a well-known notion from analysis. Agree? The question arises, however, how much this integral independent on the choice of coordinates. If we make a coordinate change, then first, so if we introduce new coordinates, x1 prime, or let me write y1, yn. Then this form, I mean not this, the form itself, can be written in terms of these coordinates. We can write this form, let it be alpha, this form alpha, which is f. F can be written as a function of y's, it is not a big deal. But then dx I becomes the sum over j dx I. This is a formula, it is well known from calculus, but also it is known from our course because we know how the differentials of functions are calculated. So this expression becomes the following. The sum over, let me write j1. No, the sum over j 1 d xi d yj1 gy1 and so on. Similar expressions. It is dx1. Also the sum over jn d yjn. Okay. Now, using the linearity of everything, we can write this in the following way. This is the sum. Well, f as before, and the sum of this and this should be, a permutation of numbers 1 and so on n, because if there are coincidences among j's, then this is 0, then the expression is 0. Here you write dx1 dx j1 dxn over dy jn, and then dy j1 dy jn. This expression, this is certainly the right expression, but it still has something undesirable, because the order of this y's is not just 1 and so on n. And it's reasonable to make a permutation, because this is the same of dy1 dyn. I write here, I think. This is the same as dy1 dyn, but with a certain sign. And this sign is 1 and negative 1, plus or minus, precisely if the permutation j1, jn is even or odd. So we can write this is equal to f yn, and here I write the sum over all the permutation of n numbers. Here I write permutation tau is this, well, j1, jn. Here I should write the signature of tau. It is plus 1 if the permutation is even and negative 1 otherwise. And here I write the product of derivatives. And here I write dy1 dyn. So this factor is is coefficient with the same expression. Now this sum, my friends. Everybody knows that this is the determinant. It is the determinant which is called the Jacobian of x's over y's, and I write it in this way. So my form alpha is f y1 yn d x1 xn over d y1 yn dy1 dyn. Now look at this and say to me what you think about the following statement. I want to say that the theorem of the coordinate change in standard calculus means precisely that the integral over u of our initial form is equal to the integral of this form. What do you think of this statement? I prefer that you say what I usually say in such cases. The statement is both right and wrong. We will not discuss why it is right, but why it is wrong. Because the formula in calculus is very slightly different. When we make the coordinate change under the sign of the integral, then do we really use the Jacobian? Or rather, we use the absolute value of the Jacobian. You can say that this difference is negligible. I can agree or not, but this is the reason why I say that this is also right. How to avoid this unpleasant situation? How to avoid this inconsistency? We have two formulas. We should have the two integrals equal to each other, but one of them contains the determinant of the Jacobian, and another one contains the Jacobian itself. What is the case when actually it is the same? Have you ever heard of such situation, that when an absolute value of a real number is equal to this real number? I personally think that this happens precisely when the number is positive. And if the number is negative, it is not wrong. It's false. So we want that this coordinate change is not arbitrary. We want that the coordinate change has positive Jacobian. This is precisely why I have to assume that our manifold is orientable. If it is not orientable, then this small circumstance will be an absolute obstacle to defining integrals. No integrals, at least of differential forms as I define them. No integrals for differential forms over non-orientable domains, non-orientable surfaces, non-orientable manifolds. Now let me continue. So how to define the integral of a form over orientable manifold? First, I suppose that the manifold is compact, simply not to mention different non-interesting thing. So how to define? We have a manifold with no global coordinate system. Then how to define the integral of this form over this manifold? Using the existing definition within the domain of coordinates. As usual, there are no different ways to handle this situation. There's only one way. We need to use what? Partition of unity. We have our manifold, right? And we have its covering by domains of local coordinates by images of the charts. Certainly we can assume without no harm in the assumption that we can assume that the domains of the charts, say balls, so some domains with compact closure, so we can really integrate the forms of them. Yes, so we have an atlas consisting of, in compact case, finitely many. In a non-compact case, we can consider a locally finite atlas, say that all the charts or all the domains are images, say, of an open ball. After this, we do what? After this, we take our form, and then we use a partition of unity. So we do what? M is, I am here denoted by UI rather the image of chart than the domain. It's not important. So UIs are open sets in M with coordinates within each of them. Then I can find functions on M with values of 0, 1, which with supports contained in U, say that the sum of I is 1. After which I say alpha is this sum, right? This form alpha I. It is 0 in the complement of UI, right? And the integral should be the integral over UI, right? So this integral is well defined, and I use the definition. Integral M alpha is the sum over I integral UI alpha I. Now, why do I use these question marks? Something seems to me here not completed. Or maybe I overstated. Really, I take alpha, it is the sum. Now, partition of unity or not important to me anymore. Alpha is the sum of the forms alpha I. And every alpha I, also differential forms also have their supports. The support of alpha I is within UI, so we can take the integral over UI. Since the form is 0 in the complement of UI, it is very reasonable to assume that the integral of M over M alpha I is equal to this integral, which we already know, which already exists, and all that. And well, if the let me begin with this case. If the manifold M is compact, then this covering is finite. So this is a finite sum. Finite sum of real numbers. Everything is well defined. But still, it seems to me that something here is not quite good. Or I overstate. What I don't like here, what bothers me, is that this definition somehow depends on the choice of this family of functions fi. And I prefer, frankly, I prefer to have functions, to have a definition which uses only the manifold with orientation. So far, by the way, it's not quite clear whether orientation is important. Only a manifold with a fixed orientation and the differential form, and no atlas, no, the more so, no partition of unity. So it should, the definition may use it, but we should somehow understand that the result does not depend on these arbitrary choices. And as soon as we understand it, we can immediately, as soon as we understand it, we can immediately decide what to do. As usual, when we want to prove that something doesn't depend on something, we say, suppose that we're given another atlas and another partition of unity. Very well. So suppose that we are given Vj and Gj with the same properties as there. Okay? And then I consider, maybe I should write alpha tilde j, Gj alpha, and the integral alpha now is defined as the sum right? And we need to understand somehow that these two things are the same. For this purpose, I want to consider a new covering or a new atlas on the manifold, which consists of all intersections of the domain Ui and the domain Vj. And I consider a new partition of unity. New coloring. Okay. Now I want to say that also I have probably I have to erase it otherwise. We have now alpha ij, which is fi gj alpha, right? Very interesting. Now, this is the same as this. I prefer actually to begin, well, why not? Which is fi alpha tilde j. It is the same of gj alpha I, right? Now, the integral over ui of alpha I, that is the integral of m, is equal to the sum right? Here I do not need to do anything related to manifolds, because ui is essentially domain in Euclidean space. And for integrals over domains in Euclidean space, we have all necessary formulas. In particular, certainly the integral of the sum of two forms is the sum of the integrals. It's not necessary to. So we have this. And this is the, so if I consider the integral over m alpha, using the first definition, we have two definitions and we want to check that they are the same. Then it becomes the sum ij, the integral over ui, uj, alpha ij. This is the first definition. This is the second definition. But the difference is that here, when we compute this, we use coordinates within which come from ui. And here we use coordinates which come from Vj. Right? These two things are the same. But the integral is calculated in terms of different coordinate systems, which you know separately from calculus. This is the same. But also we know that ui and Vj should be orientably compatible. Otherwise, things will not be equal. So, a manifold should be oriented. All u's and all v's are charts from the oriented atlas, which determines the orientation, the same orientation. And then these two expressions are the same. So the integral is well defined. Questions? Yes.
So if you had a non-orientable manifold, but you have something with compact support, then you might be able to integrate it depending on what the support is.
First of all, I didn't say about support. I will say this. Certainly, the orientation is necessary where the form is not zero. So if the form actually has a compact support which is contained in an orientable part of the manifold, that's okay, in an oriented part. Actually, I answer the question which I expected from you, Henry. If the manifold is not orientable, then actually the form should, if you really want to integrate the form, it should be defined in a different way. Because the value of the form on the vectors. Well, let me say it in this way. Probably this will be the most clear to you. That non-orientable manifolds have oriented double covers. We can have a form on the oriented double cover such that the involution which exists in double cover will change the sign of the form. So such a form which is not quite a form. It is called somehow in classical textbook in calculus, but I have to admit that I don't remember the name. So it is possible to define integral, but not of differential form, of something which is specially defined to avoid this unnecessary complication with orientations. Now, at this moment, my friends, I want to formulate, I didn't say this, but it is so clear. If your manifold is not compact, but the form has a compact cover, then this all will work. Because, again, we have a covering ui, and for only finitely many i's, this form will be non-zero within ui. For only finitely many i's, if this covering is locally finite, then for only finitely many i's, ui will have an empty intersection with the support of the form. And everything works precisely in the same way. I also want to say that the case of a manifold with a boundary is not any different from the case of manifold without boundary. So, one more small remark. We can integrate the form on the condition, which is not very convenient. The degree of the form is the same as the dimension of manifold. What is degree of the form is less than that. Then no integral exists. But there are integrals. If you take for the integration domain, not the whole manifold, but it's submanifold on appropriate dimension, precisely as the form p dx plus q dy cannot be integrated over a planar domain, but can be integrated over curves. The same here. If you have a form whose degree is not precisely the dimension of manifold, say p, which is less than n, then we can take the integrals over submanifold, because we can restrict our form to the submanifold. It is very obvious. Submanifold is embedded in the manifold. There is homomorphism of form spaces in the opposite dimension, so a form on M becomes a form on N if N is submanifold of M. One more thing. Well, you know, sometimes we speak of something very important and highly non-trivial from the philosophical point of view, but we have to discuss stupid cases. What if our manifold is zero-dimensional? Stupid case. First, but still no. First, compact. Well, it has to be finite. A form of degree 0 is just a function. So we have several points and a real number for every point. Orientation. We discussed this. It was so stupid that it is unlikely that you remember. But I said to you that orientation for zero manifolds has a separate definition. And this separate definition is the following. An orientation is a function which assigns to every component, every point, plus or minus 1. So what is the integral of a differential form of degree 0 over a zero-dimensional manifold? Yes. Integral is a sum. Sum of values of this function with the signs plus or minus, which comprise the orientation. You can say 1,000,000 times, this is a stupid case, that we should not even mention it. But in reality, it is sort of opposite. In some sense, this case is the most important. Well, at least, yes. And now the most important formula in this area, the so-called Stokes formula. In many respects, fate was unfair to the Stokes formula. It is a very important formula, but it is so short. Its proof is so obvious. So we don't know what to do. Suppose that we have a manifold M with a boundary dm, and everything is, say, compact and oriented. M is oriented, dm acquires the orientation. Now, let alpha be, so dimension of M, as you can guess, is n. Let alpha be a form of degree n minus 1. We cannot integrate alpha over M, but we can integrate d alpha over M. You can integrate alpha over dm. And the Stokes formula says that these two integrals are the same. This is the Stokes formula, that the integral, on the condition that alpha is defined on the whole M. Then the integral is differential over the boundary, of this form over the boundary, is the same as its integral. I think it's differential over the whole manifold, and this is called the Stokes formula. Very short formula, and I will prove it next time. But now I want to discuss it a little bit. Actually, you want to discuss it. I want to ask a question. Suppose that you are not familiar with this formula in this form. Maybe for some of you this assumption is sort of difficult to hold, but suppose. Do you know this formula? Maybe in some cases. I think that textbooks of calculus contain at least four particular cases of this formula. Maybe more, but these four are very notable. And the first is what? And the first is a theorem which you call the fundamental theorem of calculus. Suppose that M is the integral AB. What is dm? But M is oriented, so yes. And then the orientation of the boundary is plus here and minus here. This we know. And then what? We have a form at degree 0 on M, which is a function. We have a function f. So f actually is an element of this, or AB if you prefer. df, according to the formulas which you know very well, x is the coordinate here, is f prime dx, right? And then this formula says that the integral over M from A to B, f prime dx, is the integral of the boundary, which is f of B minus f of A. So this formula is the very first particular case of the Stokes theorem, Stokes formula. The other, what else? The formulas which I mean have names. The names certainly vary from textbook to textbook, but some of them are stable. What is the first formula? So suppose that M is a closed domain in the plane with smooth boundary, like something. Green's formula. So if alpha is p dx plus q dy, then d alpha is this. And then we have the domain with the boundary gamma oriented. Then the integral over gamma p dx plus q dy is the same as the integral over whole domain of this expression. Green's formula also becomes a particular case. Now, let me say something. I will not write anything on the board, but I will say this. There are other formulas in calculus, in multivariable calculus, which actually just follow from this. First is a formula which is called Stokes formula in the textbooks. It is formula you have a surface with boundary in space. Now in a neighborhood of this surface, you have a form of degree 1, p dx plus q dy plus r dz. And again, the formula says that the integral over the differential of this form, and differential can be easily found. It is a long expression involving 3 terms, but it is written in the calculus textbooks, is equal to the integral over the boundary of yes. And then there is a purely 3-dimensional generalization of the green formula, which is in textbook, which I know is called the Gauss-Ostrogradsky formula. Before I finish, I have slightly more than 1 minute. I want to tell you a story. There exists a theorem which sometimes is called Arnold's principle, that no theorem ever named after its discoverer. Then actually there exists an addition to this, that Arnold's principle can be applied to itself. It also was discovered not by Arnold. Yes. So what about here? We have many names. By the way, the fundamental theorem of calculus sometimes, at least in Russian textbook, which I know, is called the Newton-Leibniz formula. It was discovered before Leibniz and Newton. Barrow and Smith, there were 2 discoverers. Green formula is okay. Green was a physicist, British physicist, who is known not only by this formula, and who certainly used this formula in his works, but the formula which is called Gauss-Ostrogradsky formula, which certainly contains green formula in this particular case, was discovered before the green formula. A short note by Ostrogradsky was published some 5 years before the green formula was first appeared. As a mathematical theorem, it was published by Cauchy much later, in the 40s of the 19th century. But the most interesting thing is about Stokes formula. Do you know who Stokes is? Stokes is an outstanding British mathematician and physicist, and he was a big expert in thermodynamics. Thermodynamics say things. But as a faculty on the Trinity College in Cambridge, he had such assignment. Every year, he had to conduct a test, an exam, for some scholarship, which also has a name, but which I don't remember. He had to give several problems every year, and all his friends knew that he needs problems. And one of his friends, physicist Thomson, also known as Lord Kelvin, suggested this formula to him. Stokes, after every exam, had to publish all the problems with solutions. And he did this. So the first publication of this formula belongs to Stokes, but Stokes never said that he proved this formula. Later, Thomson published proof, and he claimed that he deduced this the works of Stokes. But still, Stokes has nothing to do with this formula. He just received it for an exam, and never claimed that he proved this formula. As to this formula, certainly it has nothing to do with Stokes. Usually it is Irigoyen, but Irigoyen was not first to prove it. At least there exists a work by Goursat, French mathematician, who actually proved this formula in this form. So see you when it's